So we're trying to come up with electron configurations for different elements, and there are three rules that you must follow. And the first one is called the Aufbau principle, and it's based on a German term meaning building up. And this one's really easy. It just means that electrons are going to exist in the lowest energy level possible, and then they build up. So if I'm looking at this diagram that you see in front of you, electrons would first fill up in the 1s orbital, and then once that is filled, then they would move to the 2s, and then the 2p, and then the 3s, and then the 3p, and so forth. Now there's a slight overlap in energy levels. If you look here on this sideline, if we want to call that the y-axis, you'll notice they don't go in numerical order all the time. Once we get into the third and fourth and beyond energy levels, we get some overlapping in energy. So notice this. We're going to fill up the 1s, 2s, 2p, 3s, 3p. That all sounds good so far. And then we move to the 4s. Whoa, the 3d, 4p, 5s, 4d, 5p. So this order is the order that electrons will always fill, from the lowest energy to the highest energy. This diagram is maybe a little more difficult to see or to remember. So I'm going to show you two ways that you can figure out what order electrons need to fill in terms of their energy. Sometimes this is referred to as the Christmas tree diagram. It doesn't really look like a Christmas tree, it's more like a triangle. But this diagram you could always generate on your own when it comes time for a test. So if you notice the way that it's written, you start with 1s and you go all the way down to 2s, and then you move over in your line and you write 2p down to 7p. Remember, the reason we don't put a 1p there is that there's no such thing as a 1p sublevel. And then you write 3d down to 6d, and you write your 4f and your 5f. So the blue number and letter combinations you write down, and then you just take your pencil real lightly and you draw through your arrows. If you're not quite understanding how I'm saying to generate this on your own, we can talk about it again in class, but this will be something that you're going to want to know. This will be very helpful when it comes for writing electron configurations later on. The second rule that you need to know is called the Pauli exclusion principles, and it gets summed up. I mean, you can learn the book terminology that no two electrons can have the same set of quantum numbers, but really what it means is when we put two electrons in the same orbital, they have to have opposite spins. And so the way that we represent that is by arrows. And when we're not writing arrows like this, the way that electron arrows get written, it's like a half arrow. So if one electron has an up spin or a positive spin, then the other electron must have a negative spin. And if you wanted to refer to that as in your quantum numbers, that fourth quantum number, that electrons either have a positive 1/2 or negative 1/2 value. So that's what that means. So we can never have two electrons with the same spin in a diagram or an electron configuration. That can't happen. So we always want to show them as existing as opposite spins. That rule is pretty easy. Our third rule is called Hund's rule, and this just says that when we put electrons into orbitals that have multiple values, for example, in a p orbital, there are three possible orientations for a p orbital. It refers to the orientation around the x-axis. This would be the x, the y, and the z. That you must have each orbital have one electron before you can double up. So what that means is if I'm filling up electrons, so there's 1 electron, 2 electrons, 3 electrons, 4 electrons. If I'm trying to put 6 electrons in this orbital diagram, I have to put 1 in each of the orbitals before I can partner them up. So I'd have to put 1, 2, 3 electrons in that order before I can start doubling them up and putting a double electron in those orbitals. So what you can't have is you can't have 1, 2, 3 electrons if this is an orbital diagram. So that can't happen. So we've got three rules. We've got Aufbau principle that says we have to start with the lowest energy level possible and fill up. We have the Pauli exclusion principle that says that when we are showing our electrons in the orbital diagrams, they have to have opposite spins. And then the third rule is this Hund's rule that each orbital has to have one electron in it before we can go back and double it up. All right, so we're going to put this into practice. What we are going to do is pick some samples of elements, some simple ones at first, and we're going to do two things with them. We're going to draw out what's called the orbital diagram, and then from that we're going to do the shorthand that's called the electron configuration. So I'm going to start with this more complicated looking orbital diagram. This should look like the one that was a little more colorful earlier. This just shows how the energy increases as you move away from the nucleus, as these quantum numbers get bigger. And then here's the nucleus. Now this is greatly enlarged, but that's okay. So the example we're going to start with is hydrogen. So I go to my periodic table and I look up the atomic number for hydrogen, and I realize that it's 1, and that means that in a neutral situation, hydrogen would have 1 electron. So all of this work that we've been talking about basically boils down to this. Where is that 1 electron? We follow our 3 rules that we just learned. So you start with the Aufbau principle, and we place the electron in the lowest energy level possible, and that would be down here in the 1s. And now I'm done. I don't have to worry about Pauli's exclusion principle because I only have 1 electron, and the same thing for Hund's rule. So now I have just done the orbital diagram for hydrogen. If you were drawing this on your own, which will be most of the time, the way that you do that is you would just you draw your dash and you draw your 1s, and then you draw your arrow representing your electron. And then I'm done. This is the orbital diagram for hydrogen. The other thing that we do now is we write what's called the electron configuration. And basically this is just the shorthand way of doing the orbital diagram. So the electron configuration is the energy level, the sublevel, and how many electrons are in there. So the electron configuration for hydrogen is 1s1. Let's do some more. We're going to do the same thing for helium, the orbital diagram and the electron configuration. Helium has atomic number 2, so it has 2 electrons. We're going to figure out where those 2 electrons are. Start in the lowest energy level possible. I put 1, and then I put 2. And then that energy level is full. Remember, each of these suborbitals, these sublevels, can hold 2 electrons, each with opposite spin. So I'm done with the orbital diagram, and now comes time for writing the electron configuration for helium. It's 1s2. First energy level, sublevel shape is s. There are 2 electrons in the s orbital, and now I'm done. Hopefully you're starting to see the pattern here. Now let's look at lithium. Atomic number 3, which means it has 3 electrons. We follow all the rules. Start at the lowest energy level possible. I put 1, I put 2. Now the 1s level is full, but I still have 1 more electron to place in the orbital diagram. So now, according to Aufbau's principle, now I move up to the next available energy level, which is the 2s level, and I put my 3rd electron. And now I'm done with the orbital diagram. Electron configuration would be 1s2, 2s1. Notice with these superscripts, I hate to call them exponents, but notice with these superscripts, if I add them up, I get how many electrons are in the element. It's just a quick way of checking to make sure that you haven't lost any electrons along the way.